Okay. What? No, and I won't take off 5. Where's Alexia? She's always absent, like all the time. No, she's never here. You should go in that. Okay, so we are going to continue with related rates. We started last time. Hopefully you have the handouts. I also have your tests to give back, but I'll give those back at the end of the class. And you guys should check the solutions because a lot of you just did things the hard way for some reason. Saw people using quotient rule when they didn't even need to use quotient rule and all sorts of stuff.
We remember the fact that there was a joke about
Continue on to the rates. Oh, we start related rates. I think we did 2 examples. We did the cylinder one, and we did the ladder one, right?
Yeah.
We did the one with the ships too.
And we did the one with the ship.
Yeah.
Okay, so let's do number 2 then. I don't think we did that. We didn't do number 2? I don't think we did 2. So the handout, we lost it. There's a copy of this on the web page, so
this.
download it. Gonna do example 2. Okay. So again, we've been over this. Related rate problems, they always have these same 6 steps in that order. Sometimes some of the steps can be done for you though, but you still check things in that order. And in problem 2, that is the case. Some of these steps are actually done for you. So again, we're going to do step 1. We're going to read the problem carefully. So it says a particle is moving, part A, problem 2, part A. A particle is moving along the curve y equals x cubed plus 1 in such a way that the y coordinate is increasing at a rate of 2 units per second. And at what rate is the x coordinate changing when y equals 9? So that's the problem. So step 1 is to read, so we kind of understand the situation. Step 2 is to draw a diagram. Now here we can kind of skip this. Right? Why? The whole point of the diagram is to be able to figure out the equation you want to use, right, for step 4. They already gave me the relationship as an equation. So they already told me that y is equal to x cubed plus 1. I know the equation. I don't need a diagram to figure out the equation. So I still go through step 2, but here I realize it's not necessary to draw a diagram, right? Because the whole point of doing that would be to get an equation that I already have. So now we'll just go to step 3. Step 3 would be to write down the given information. Write down what you know and what you want to find in terms of rates. So what do we know so far?
Y equals x cubed plus 1.
I know how fast the y coordinate is changing. They told me that it's changing at 2 units per second. It's increasing, which means it's a plus 2 because it's increasing. What do we want? We want dx dt. When do we want it? Now. We we wanted, when y is equal to 9 is what we want that, right? Now we move on to step 4. Step 4 is to just have an equation that relates all the variables that we need to worry about, which is an equation relating x and y, but we were given that equation. Y is equal to x cubed plus 1. Step 5. Differentiate implicitly with respect to t. Derivative of y is dy dt, or y prime.
3x squared plus dt.
Or x prime. Derivative of 1?
0.
0. So that's our relationship. So now we said, this guy actually know, right? That's the 2. The dx dt is what I want to find, but I don't know what the x is. So I need to find x. How do I find x?
Plug in.
Right. So remember, in step 5, if there's anything that you don't know, you need to go back to step 4 and find that guy using the original relationship. So now I know that y equals 9, so I'm just going to plug 9 in. So I'm going to get x equals 2. That brings me to step 6, where I'm going to start plugging in everything that I know, solve for what I want to find. So my dy dt is 2. And that's equal to 3 times x squared, which is 2 squared times dx dt. Which means my dx dt is equal to 2 divided by 3 times 2 squared. 2's cancelled, so it's number 6. I.e., the x component is increasing at a rate of 0.6, whatever units per second they give it to us. That's it. Questions on that? So basically what this is, we could actually draw a diagram if we wanted to. That's x cubed plus 1. And this is saying when my x is 2, what's happening is my y coordinate is increasing, which means I'm moving up, and my x coordinate is increasing, which means I'm moving to the right. So the particle is actually moving in that direction along the curve. It's moving up like that. No. You do what you're asked for. So they asked me for dx dt, I found dx dt. Let's look at part B. No, forget part B. So I think I want to do problems 5 and 7. Those are some nice problems to do. They're very test and quiz friendly.
You don't need to know part B?
No, don't worry. Let's move on to example 5. So a baseball diamond is a square with side 90 feet. The batter hits the ball and runs towards first base with a speed of 24 feet per second. He runs really fast. At what rate is his distance from the second base decreasing when he's halfway to first base? Okay, so step 1. Read the problem. Okay, so we have a baseball diamond. He hits the ball and he's running to first base. and we want to figure out his rate of change from the second base. Okay, cool. Step 2. What? Diagram. What would the diagram look like? Well, it's a baseball diagram, which is a square. Hopefully you know about baseball. That would be where home is. This would be first base, second base, third base. Yeah. It's an American pastime. It's baseball. Okay. So that hits the ball here. He runs towards first base, right? So pretend this point is the guy, and he's running that way, right? So that's him, and he's running in this direction. And what do we want to know? At what rate is his distance from the second base decreasing when he's halfway to first base? Okay, so assuming that this is the guy running along that line, what would describe his distance to second base?
His distance to
The
second
whole
base.
thing from second base minus.
So that would be like a triangle?
Huh?
That'd be like
Right, you connect this with a line, right? Right? At any given time, his distance from second base is just a straight line connecting him to second base, right? So this is going to be our diagram, right? So now, the important part of this diagram is we're going to start labeling things. How are we going to want to label things? But you see here, this is a nice little right triangle here, so probably I'll want to be able to use that, right? Because I know equations that deal with right triangles. So I'll probably want to use that instead of this guy, which is more complicated to work with. So let's start labeling these sides. What is this side here? 90. It's 90, right? And it's always going to be 90, so I label it with a constant. This length, though, is changing, right? As he moves along this line, the line is the longest when it's here, but it gets shorter as he's moving here. So this line here is actually changing. Call that Y. Right? This one here is also changing as he moves towards that, so let's call that X. Which means my diagram now looks like this. That's my X, that's my Y, that's my... Okay. So that is step 2. Step 3, what do we know, what do we want? Right, dx dt. I know how fast the guy is running, so I know how fast this distance is moving. Nope. It's negative 24. Why is it negative 24? Notice that as he's running towards this, x is decreasing, right? That's why we read the column carefully. It's important for you to know that it's a decreasing thing. You need to look at the diagram and really analyze the situation. Okay, so it's negative because x is actually getting smaller as he's running here. So it's decreasing, so that negative is actually important. Because that length x is decreasing. According to the way I set up my diagram. Okay. Now what do we want? I want to find out y prime, that's how fast his distance from second base is increasing. When do we want it?
When he's halfway to the first base.
Okay, how would I describe that situation? Right. Since this whole length here is 90, when he has run 40, when x is 45, that's halfway. So this is what I want to find. I want to find his rate of change from the second of the distance from the second base when x is 45. So that's what I want. Step 4. Equation. What's going to be the equation? Now we're at step 4. Step 4, I have to come up with an equation that relates all my variables. My equation is, of course, going to be informed by this diagram, which is going to give me right, Pythagoras' theorem. is the nice thing about that is we don't do trig in this class, so every time you see a right triangle, we're going to use Pythagoras' theorem and not SOHCAHTOA. Right? So now we have that. What's the next step? Differentiate. What do we get?
Equals to 2.
Okay, so I can divide both sides by 2. And I actually want to find dy dt, so I can actually solve for dy dt. That is going to be x dt divided by y. So, do I have everything I need here? Well, I know x is 45. I know my dx dt is minus 24. The y I don't know. Y I have to find. So now I go back to equation to step 4, not this step 4. So this y I want to figure out, go back to that original equation and start plugging in numbers. So I go here. So I know that when x equals 45, this means 45 squared plus 90 squared equals y squared. How do I solve for y? Okay, how do I do that? Using my brain. Well, hopefully we all use our brains, yeah. Go, how?
Yeah, what's 90 squared?
90.
That's 45 times.
90 is 2 times 45, right?
3 times. So it'll be 3 times 45.
So that would be 45 squared plus, when I square, the powers distribute across each term. So it's actually 4 times 45 squared. Right? So at 45 squared plus 4 times 45 squared, that gives me 5 times 45 squared.
You basically just broke the 90 and added.
I broke the 90 to 2 times 45. If I have 2 times 45 raised to the square, it means I raise each part to the square. Because a times b all squared is a squared times b squared. So I get this. Now I have x plus 4x. 5x. Okay. So now, my y would be just the square root of that. Which means that's radical 5, radical 45 squared. The square root gets rid of that. So now I have 45 radical 5. Or you can find 90 squared and 45 squared and add them together and then figure it out. Okay, so now where are we? Here. Now we go back here in step 6, we're going to start plugging everything in. That's my dy dt. My x is 45. My dx dt is minus 24. And my y is 45 square root of 5. So now my 45 is cancelled. Let's get minus 24 with the radical 5. And so notice that y is decreasing. Minus 24 over radical 5 feet per second. And here's B. Now B goes back to the same situation. And B asks the question, what's his distance from third base increasing at that same moment? So again, he's right here. His distance from third base would be the distance here. So that's first, second. Okay.
That's how it's done.
So now what?
Yeah, label times.
Relabel, right? So make this 90. This I can call y, now that I can call x. So I have this diagram now. 90, y, x. Yes, this will be step 2. And now we go to step 3. Now you put in what you know, what you want. So I know that dx dt is 24. In this situation, I put a positive 24 because the way I label the x now, he's running that way, which means my x is increasing. So now it's a positive 24. And I want dy dt when x equals 45. Which, by the way, notice that this would mean that my y is 45 right 5. Right? Because it's actually symmetrical too. Right? He's halfway, so we have symmetry. So the same length that y is going to be at the same moment here, was the same one it's going to be right there. And so we get exactly the same equation. Almost the same thing.
Except for negative is not negative.
Right, except that negative 24 was a positive 24. So here when we go to step 5, 2 x t equals dy dt. So means that dy dt is equal to x dx dt over y. Means that dy dt is plug in the x, plug in the dx dt, plug in the y. So now I just get the positive answer. Worked out nicer because of symmetry. We were exactly halfway. Questions? Another example. Let's do example 7. And on the next page, I have more examples for you guys to try. Some of them are actually from past finals, so you can see. But we're going to do 7 and then move on. Superman is cruising at 390 feet per second at an altitude of 5,000 feet, and he flies directly over Jhevon's house. Assuming Superman maintains altitude and speed, how fast is the distance from Jhevon's house to Superman changing at the time when Superman is 13,000 feet from Jhevon's house? Okay, so very similar to a quiz problem that we had that plane flying over the radar tower, so it's a very similar situation. First thing you do, read the problem carefully so you understand the situation. 2, start to draw a diagram, right? So this would be the ground. here, John's house. Lying above is Superman. Okay. Now that height here, it's 5,000 feet. And he's maintaining that altitude. Right? Okay. So now let's suppose Superman is over here. What's the distance from Superman to Jhevon's house? It's just a line connecting, it's a straight line connecting Jhevon's house to Superman, right? Which gives us this height here. And so what's our diagram here? Again, it's another right triangle, right? Kind of the same diagram show all the time. Very similar. So there's our right triangle. Now we're going to start labeling that guy. So, is this changing? No, he's maintaining altitude. So that's 5,000. Label it with a constant. Is this changing? Yes, because Superman is moving. So this distance is actually increasing. So call that something like x. Is this changing?
Yes.
Yes, because he's moving here, it's also getting longer. Call that y. Which means that's my diagram. Step 3. What do we know? What do we want?
You know the DXD.
I know dx dt. I know how fast Superman is flying, so I know how fast this distance is changing. He's flying at what, 390? It's positive 390 because x is increasing in this scenario. What do we want? Well, dy dt. When y equals 13,000. Right. So it's when his distance from the house is 13,000, so that's the y value. Okay. Now move on to step 4. Equation. So that's my diagram. What's the equation? X squared plus
5,000 equals y squared.
5. Differentiate. Okay, so at this point, I know dx dt and I know y.
So for x.
I need to find x. So I'm going to try to find x using that original equation. I know that x squared plus 5,000 squared is equal to 13,000 squared. This means x equals it's a special triangle. Huh? Remember there was a thing when this was 13 and then this is 5, that would be? Alright, 5, 12, 13 triangle. You take 12 squared, which is 144, add 5 squared, which is 25, you get 169, which is 13 squared. So I know that here my x is just 12,000, right? Everything's bumped up by a factor of 1,000, so my 12 is bumped up by a factor of 1,000, that's my x value. So now I can move on to step 6, where I'm going to plug in everyone. So this means that dy dt is equal to my x value 12,000 times dx dt, 390 divided by my y value, which is 13,000. So that, 13 goes into 39 actually, right? So that goes to 30. And so now I have 12 times 30. 12 times 3 is 36. So that gives me 360. Is that a funny number? So that's feet per second. But I don't really care about the units. Like this? No. Yep, that's basically what we want to cover for related rates. Try the other examples on your own. But as you can see, like all these problems, I go through exactly the same 6 steps all the time. Right? So it's one of those things that you kind of get into a groove for if you practice enough. So you can redo the problems that we did in class and try the other ones that we didn't do. That's kind of it for related rates. Any questions on any? Yeah. Where? Here?
When we found the derivative, and then we came into here, the x squared plus 5. You don't put in the 13 on the y squared. The 13. You don't put it.
Oh, I did. Right, so at this point, I knew what the y value was. I didn't know the x value. Right? So I go to that equation in step 4, x squared plus 5,000 equals y squared, and I plug in the y value, which I knew was 13,000. So I plug that in here. And then I remember that there's a special relationship, 5, 12, 13. So those are the 2 relationships you need to know. 3, 4, 5, and 5, 12, 13. Right? So it's something that we shows up, it's very common. Right? So I realize here's a 5, here's a 13, that guy must be a 12. Right? And everyone's multiplied by 1,000, so 12 is also multiplied by 1,000. And then I plug in everything here.
When you're written on coding, like you say you have 5,000, is the one that's always a constant?
What's always the constant?
And like you know what y was, but you use 5,000 because 5,000 is your constant.
No, 5,000 was just there from the original equation. Right? I don't really care what's a constant from what's not. I just know 4 is the equation that governs everything. Right? So if there's anything I need to find, I go back to equation 4. Right? It happens to be a constant by how the problem is set up. It doesn't have to be a constant. I know it's a constant here because we're told that he maintains altitude, so he doesn't, that 5,000 stays 5,000.
So the only time something you put some under like dy dx, it gives you like something per second.
Come in?
Like the only time you would differentiate like an x or y value if it's the problem tells you it's changing by something per second, like feet per second or meter per second.
Well, feet per second or meter per second is a unit of speed or velocity, which we know comes from the first derivative.
Yeah.
So that's what tells you you had to differentiate to plug those numbers in. Which is, again, it's another thing that hints to you as related rates. So just to recap, how do you know that it's a related rates problem in the first place? Is they describe a situation and tell you the rate of change of one of the quantities. the time we get to the final, there are going to be tons of different word problems, so you really want to know which one is hinting towards which topic, right? Or one or several quantities, right? And that is going to be in units of, it's going to be something per time, right? So it could be feet per second, miles per hour, something like that, right? So that would be actually mentioned in the problem. And then 2, they're going to ask you to find another rate. Right? So once you read a word problem and you realize that's kind of what's going on, you know it's a related rates problem. So they're going to tell you something is going on. They're going to tell you the rate of change of one of these things. Then they're going to say, find the rate at which this other thing is changing. Right? Once you know that, and the units is this, you know it's a related rates problem, you just go into related rates mode, do these 6 steps.
You guys do like demand functions?
With
exam? This. Because there's one in the book that I had issues with.
I think there was an example here. Yeah, if you look at problem 6 in this example, it's a problem with a demand function, right? But you still recognize it. So remember, we also talk about demand function when we're doing marginal analysis, right? Like marginal cost and that sort of stuff. But the thing is, how you know this is a related rates problem and not a marginal cost problem is because it tells you a rate of change, right? So it tells you a demand function, which is this, which means you don't need a diagram in this case because they just gave you the equation. And it says, how fast is the rate of sales changing when the price is this? And it tells you another rate. Right? So it tells you the price is decreasing at a rate of 40 cents per week, and it asks you what is the rate of change of something else. So you know it's a related rates problem. So again, you're going to go through the steps. You already know the equation. P plus 2x equals plus xp equals 38. And then you're going to just differentiate and plug in the numbers.
The one they have in this book, they give you like a domain. They said 0 is less than or equal to q, less than or equal to 800. So it's like, I don't know how to work around that.
Oh, well, that's just giving you a restriction, so you know that you can't plug in anything too small or too big.
Oh, okay.
It's not really something that would affect you the working on.
Okay.
It's just that if you get an answer outside that range, you know ignore it. So there's nothing else to do with that. But you go through the same 6 steps. But I wouldn't ask about a demand problem. The problem's going to be very similar to one like I did here.
What's the difference?
Huh?
What's the difference?
Between what?
The demand and like what you're doing?
There is no difference. There's no difference. You go through the same 6 steps. Once you realize it's a related rates problem, you go through those 6 steps. It'll never change. Don't think, oh, it's going to be a surprise. No. Once you know it's a related rates problem, once this is the kind of situation you have, go through those 6 steps.
Yeah, for the
It doesn't matter if you're talking about a demand function or whatever they throw at you, it doesn't matter. Those are the steps to it.
I mean, the only thing, I think the only difference would be like, you don't have to guess like, I mean, you don't have to know like a specific equation, it's already given.
Right, with the demand function they'll give you, because it's something you can't figure out.
Yeah.
Right? So that would be sort of like example 2, would be the same thing, where they just gave you an equation, so there's no diagram to draw, so you skip step 2, but everything else you go through, because they give you the equation.
So that's the difference.
It's not really a difference, it's,
Yeah.
you just skip step 2.
It's a difference.
You gotta remember that geometry.
But you can try the rest of those on your own to make sure you actually understand. And next class, or when we're reviewing for the 3rd test, you can ask me questions. Right now, we're going to move on.
Wait, when's this next exam?
the curve sketch.
What is today?
What?
Did you just give us, this is.
We're not gonna finish this tonight.
Okay, good. So like 2 weeks on?
So I think, so after curve sketching, I think we also have optimization. And then the test.
So like the old chapter 4 pretty much?
So let's see.
But we don't want it like close, because I know it's 2 exams are close to power, right?
Yes.
So can you put them 2 close together?
So I think,
Make sure that
so curve sketching will probably take in a couple classes. So I'll probably finish up curve sketching by Monday, by Tuesday, next week Tuesday. And then Thursday I can do most of optimization, so it'll probably be the following Thursday. So 2 Thursdays from this week Thursday, approximately. So we'll keep the Thursdays, unless that's Thanksgiving. It's, yeah. In which case, if that's Thanksgiving, then it's after Thanksgiving. So you're gonna be at Thanksgiving dinner. When they go around the table, what are you thankful for? You break out in tears. Okay, so. We're going to move on to 4.2, maximum and minimum values. So conceptually we've spoken about these before, but we're going to get more specific now. About some definitions. We're going to talk about 2 kinds of maximum and minimum values. There's what's called the absolute maximum and minimum, and there's what's called the local maximum and minimum. Let's first talk about the absolute maximum and minimum. So, let's see. Say f x is on and it can be open. It can be everything, like negative into positive infinity. Then if there is a C such that f of C is greater than or equal to f of x, all x in the domain. Then f of C is called the absolute max. I'll describe what this means. If there is C such that f of C is less than or equal to f of x for all x in the domain, then f of C is called the absolute minimum. Right? So basically, the biggest value of all the y values is called the absolute max. The smallest value of all the y values is called the absolute min. Notice that these do not have to exist. I'm going to give you some examples of graphs, and we're going to talk about how to find the absolute max or min of these graphs. So let's say that's one graph. That's another graph. That's another graph. That's another graph. That's another graph. Okay, so basically what the definition say is absolute max is talking about the largest y value in general, right? Absolute min is talking about the smallest y value in general. Okay, so this is my function. Where would the absolute max be located?
At the tip top.
Right at this top, right? At that point, the y value at that point is larger than every other y value. Right? So that point here would be called the absolute max. Right? Whatever that value is. Right? So if this is at like C, then I would say f of C equals the absolute max. Now, is there a smallest y value in general?
0.
0 is the smallest y value, right? These 2 points are the smallest values. So this guy here is an absolute min, right? So I can call this A and B. So in other words, I'd say f of B is the absolute min. But actually, f of A is also an absolute min. Right? Because they actually both are 0. And that's basically it. You're looking for the y value that's the biggest out of everybody, and the x value, or the y value that's the smallest out of everybody. The biggest guy is the absolute max, the smallest guy is the absolute min. What about this guy?
Okay, this is the top.
So right here, that's your absolute max. Right here, that's your absolute min. That's it. Biggest y value, smallest y value. What about here?
It doesn't exist.
Notice that this has no absolute max, right? Why does it not have an absolute max?
So it goes infinity.
There is no biggest y value, right? The graph just keeps going up. There's no y value that I can say, this y value is the biggest one. It keeps going up. So in this case, the absolute max does not exist. What about the absolute min?
0.
It's going to be 0, right? This is actually filled in. So that's a y value. That's going to give us the absolute min. Okay, what about this one? There's no absolute max. And there's also no absolute min. Right? There is no largest y value because the graph keeps going up. There is no smallest y value because the graph keeps going down. Right? Any y value you pick, you'll eventually get smaller or bigger. Right? So there's none here.
How come the one, like, for the ones that don't have either a max or minimum, they have asymptotes? Does that have anything to do with it?
No, I don't need to have asymptotes. I could accomplish the same thing if, for example, this was a hole. Then there'd be no absolute max there either, right? Because it means I'm approaching that y value, but I'll never actually get there. So you don't have to have asymptotes. It's one of the easiest examples I can pick. Right? So it just means that, is there a y value that's bigger than everyone? Or is there a y value that's smaller than everyone? That's what we care about. What about this one? So this dot here is the absolute max. And this middle one here, that's your absolute min. That's it. Okay. So as a picture, that's what's going on. You're looking for who's the highest or who's the lowest, right? Which may or may not exist. It could be the case that there's no highest guy or there's no lowest guy. But if they do exist, you need to be able to pick them, point them out. Now let's talk about some theorems, as well as some other definitions. There's something called the extreme value theorem. It says the following. If our function is continuous on a closed interval AB, then f must attain an absolute max and an absolute min on AB. Right? So, as we point out in this example, it's possible for a graph not to have an absolute max or a min. However, in this situation, if you're continuous on a closed interval, you have to have an absolute max or a min. You have no choice. So in this scenario where your f is continuous on some closed interval, you have to have a max or a min, and of course we'd like to be able to find it. There's also something called Jhevon's theorem. Not the last theorem, these theorems. And it says the following. If f of x has a max or min at x equals c, and f prime of c exists, then it turns out that the derivative at a max or min, if it exists, it actually will always be 0. You don't really need to know how to code those two theorems, but they're going to be important for the methods that I'm going to set up. So basically, if you're continuous on a closed interval, you have to have an absolute max and min. And Jhevon's theorem is going to help us find it. Because there is a certain pattern. I want to know two things though. One thing I want you to notice is that the theorem doesn't work in reverse. So it is not true that if I know the derivative is 0, it has to be a maximum or a minimum. Example, y equals x cubed. Right? If I look at that function, it actually doesn't have a max or a min. Right? However, if I take y prime, I get 3x squared. And if I set 3x squared equals 0, I get x equals 0. So the derivative is 0 at this point, but it's not a maximum or a minimum. Right? So the theorem doesn't work in the opposite direction. Right? I know that the first part is true, then this part must be true. But it's not true if this is true, then that part is true. So that's the first thing. Second, remember, it's possible for the derivative to not exist. Even when example of that is, of course, absolute value of x. Look at absolute value of x, that's the d function. Notice at this point here, you have a minimum. But f prime does not exist. We actually proved that f prime doesn't exist at 0 for the absolute value. So you can't have a minimum even though your derivative is not 0. So examples like these is why something like the first derivative test is going to be important for us, which I'll show you guys later in a bit. Yes?
What's the difference between absolute value of x?
Oh, it changes. It's either +1 or -1. Because remember, absolute value is a piecewise function. So it's x of x is greater than 0, it's minus x of x is less than 0. So the derivative is also a piecewise function. It's 1 if you're in this on the right side of the y-axis, and it's -1 if you're on the left side of the y-axis. So the derivative breaks into pieces when the function breaks into pieces. Okay. More definitions. Because these things worry us, right? That we're not, how do we know we're going to be a maximum or minimum? So we're going to try to figure out how we can identify these points, because they're going to be very important. So we're going to come with another definition. So, a number C is called a critical number if f prime of C equals 0 or f prime of C is undefined. So points like that, I'm going to want to be able to find. Points like this, I'm going to want to be able to find. So there are two situations that I'm going to always be checking. And that's called a critical number. A critical point is a coordinate. It's the coordinate where the xi is a critical number. C, comma, f of C. So a number is critical if the derivative is 0 there or it's undefined there. Right? Those are things that we're going to want to pay attention to. You're going to see why soon. That's actually an important definition to know. To know where to find a critical point or critical number. There are many things we're going to want to do, where one of the steps in doing them is to find the critical number. So you're going to need to know that definition. It's very important. Those are some ideas you'll have bouncing around in your head for a while. Right now, let's go into some calculations. Let's cut to the chase. How do we find an absolute maximum? It turns out that there's something called a closed interval method. So suppose f of x is continuous on closed absolute max or min by the way, these guys are guaranteed to exist because this is true, by the extreme value thing. By using, it's called the closed interval method. So, one of the problems that you'll be asked on the test and on the final is, here's a function on this interval, find the absolute max and min, right? And what you're going to do is the closed interval method. It's one method, 3 steps, it's always the same thing that you do. First thing, find the critical numbers. Evaluate f at these numbers. So that's going to be step 1. You're going to find all the critical numbers and find what the function is at those numbers. Right? So you're going to find all points where your derivative is 0 or undefined. You're going to take those numbers, you're going to plug into f, and you're going to get some y values. 2. We're going to evaluate f at the endpoints. I.e., we're going to find f of a and f of b. That's going to be the second step. 3. The third step is you're going to compare all the y values you found. The largest y value is the absolute max. And the smallest y value is the absolute min. That method is called the closed interval method. What? I'm going to give you several examples. So let's actually do some examples of the closed interval method. Actually, before that, I told you how to find local maximum. Then I gave you examples. Hopefully that time for the examples. I'll leave you guys in suspense on for like 2 weeks. So, I have to define what's a local maximum. So remember, the absolute maximum min was the biggest guy in general, or the smallest guy in general. Local maximum is just talking about the biggest guy in some small local region, or the smallest guy in some small local region. So let's say, if f of c is greater values near C, then f of C is called a local max. If f of C is smaller than f of x for all x near C, and f of C is called a local minimum. Let me give you illustrations in minutes. Then I'll tell you how to find those guys. So this guy, so So last time we saw that this guy here was the absolute max. These two were absolute mins, right? So these are the smallest guys in general. This was the largest guy in general, so that's your absolute max. These are absolute min. Now when you're talking about local, you don't care about in general per se, you just care about in some small surrounding region, right? Now if you look at this guy in this small surrounding region, this point is still the smallest in that region, right? So it's also the local max.
Did they give you like an interval in a problem like this?
Yeah, in general, you'll get intervals. I just want to explain that idea so well. Again, here, the same thing that actually applies. This is also a local maximum. You see the differences soon. Again, here, because it's some local region, this is the smallest. It's the absolute min, and it's also local. Here, it's an absolute max. There is also a local max. Sarah says, they look like it's the same thing all the time. Not the same all the time. Jump to this graph. Look at that point. How do you describe that point? Notice that in a very small region, it's the smallest guy there, right? If you look close, right? This is a local minimum. Is it the absolute minimum? The answer is no, because there's someone with a smaller y value than that in general, right? So this is a local minimum, not an absolute minimum. If I look here, how do you describe that point? Well, that would be a local maximum, right? But it's not an absolute maximum, because there's another guy that's bigger than that guy. However, in this small region here, he's the biggest, right? So that's the difference between local and absolute. Absolute is talking about in general. Local means you're zooming in, and in that little region, he's the biggest or the smallest. Similarly here, this guy is a local minimum, because in that region, he's the smallest. He's not the smallest in general, so he's not an absolute minimum. This guy here is a local min and an absolute min, right? Locally that region he's the smallest, but also he's the smallest in general, right? So he's both local and absolute.
I have a question.
Yes.
So, absolute min or max would be,
Absolute means in general. You're looking at the entire picture.
so if it's absolute, then that means it's local.
Absolute is automatically a local, yes. But not all locals are absolute.
Yeah.
And you could have many local minimums or max.
And you can have several, yes. For example, this is a local max, that is also a local max, right? Because in that region, he's the biggest. So local is like when you're zooming in, who's the biggest and who's the smallest. Absolute is when you're looking at the whole picture in general, who's the biggest, who's the smallest. If you look at this guy, it had no absolute max. It also has no local max as well, right? There is no region where I zoom in and there's a y value that's bigger than all of the y values. So again, here this has no absolute min. It also has no local min. So that's the difference between absolute and local. Just so you don't confuse, I want to tell you some other names for them. Absolute max and min, they're sometimes called global maximums and minimums. Right? Global is kind of like you're looking at the whole thing. Whereas if we talk about local max and min, your textbook might also call those relative maximums or minimums. Right? So it's just a different terminology for the same thing. You see the word extreme value? It just means a max or min value. You see the word extrema, it's just the plural for extreme. So for example, you might see this phrase. Absolute extremum that's just the same as saying the absolute maximums and minimums. Or if they say local extrema, they're talking about local maximums. I tried to get to the examples, but I don't think I'll get to the example. Too much theory. Okay, so there are two main ways to find local max and mins. The first is called the first derivative test. And it goes to follow. Step one. Find all critical numbers. Right? This involves taking the first derivative. That's why it's called the first derivative test. Right? 2. These on the number line. 3. Test the intervals. Find out where f prime is positive or f prime is negative. Classify based on the following behavior. So let's say you're on a number line. I give you a function, you find all the critical points, so you find the derivative set equal to 0 undefined, you get all these numbers, right? You're going to plot them on a number line. So let's say here, x1, x2, these are critical points.
Can you open the board a little bit? I can't see the bottom.
Critical point. Okay. Now when I say test the interval, what you mean, you're going to plug in a number over here into the first derivative. We're going to actually practice some of these, but I just want you to get the idea. I'm going to pick a random number over here. It actually doesn't matter which number you pick one that's nice to plug in. All right? And you're going to plug in here into the first derivative. Now, if you get a positive number, what does that mean?
It means it's increasing.
It means it's increasing. It means the first derivative is positive on that interval, which means you're increasing. Plug in a number over here, and let's say you get a negative number. That means it's decreasing. Now this guy here, notice that you're increasing and then decreasing. So this point, if it's on your graph, this would be a maximum, right? So here, if f of x1 exists, it's a maximum. In fact, it's a what we call a local maximum. For absolute max, you use the closed interval method, which I did before. You wouldn't do this. Depends on what you want to find. Right? This is how you, if you're looking for a local, this is how you do it. Right? So you find all the numbers where the derivative is 0 or undefined, put them on a number line, test each interval in between them. Right? Now if your function is continuous here, and you're increasing and then decreasing, it means you hit a maximum point here. If you test this guy, and that's positive, it goes up. And you're continuous here. If you're decreasing and then increasing, that means you would have hit a minimum here. If f of x2 exists, it's a local mean. In any other situation, it's neither. Yes.
Like, when you mean it doesn't exist, if it's a critical for the, does it not mean it exists?
No, the critical point is where the derivative is 0 or 1. What, you mean this here?
Yeah, you said if it exists.
Right, it doesn't have to exist. Right? But I could be, for example, an asymptote, like 1 over x squared. Right? At x equals 0, the derivative doesn't exist, but I don't have a maximum there, because the function itself doesn't exist. Right? So I need the function itself to exist there to even talk about max or mins. Right? So that gets me out of the asymptote situation. Right? So So I need to know that my function is actually continuous there, and then I can know if you're increasing on the left and decreasing on the right, you're a maximum. That is and that's the first derivative test. So this is how you classify a maximum point. This is how you classify a minimum point. Any other behavior is neither. So that means if your function doesn't exist at that point, which is possible, it's not a max or a min. Or if it doesn't go down and then up, or up and then down, it's not a max or min, right? So you might do these tests, right? And you might have a point where you're going up here and then you're going up here. It's not going to be a max or a min, right? Or you could have this situation where you're going down on this side and you go down on the other side. It's not a max or a min. Or you might have a situation where you're going up here and down here, but it's here, f does not exist. It's not a maximum, right? So in any other situation other than these two, it's neither. But this is what a maximum looks like, this is what a minimum looks like. And we do not have time for examples, we have to pick this up on Wednesday. I have your test to give back though. And also a quiz. So we'll stop now, we'll pick this up on Wednesday with some examples. And yeah. So remember the last day to drop is Thursday. So if you did bad, you should talk to me. Doing bad means getting less than a 70. Less than a 70.